Hello viewers, welcome to my channel. Today we shall solve a problem on moment of inertia. Here the problem is we have to find out, we have to prove that the moment of inertia of an elliptical lamina about its any tangent which is parallel to its any diameter whose equation is y equal to tan theta x, tan theta is not equal to 0 or infinity, 0 and infinity is 5 over 4 mp square, where m is the mass of the lamina and p is the perpendicular distance of the tangent from the center of the lamina. So we have to prove this. Now let's start. Here at first we consider the equation of the ellipse as x square over v square, y square over v square equal to 1. This is the equation of the ellipse and also the tangent at any point a cos alpha b sin alpha is equation of tangent is x cos alpha over a plus y sin alpha over b equal to 1. This is the equation of tangent. This is the equation of ellipse. And this is the equation of its diameter, which is other than major axis or minor axis, that is tan theta not equal to 0 and infinity. This is the tangent, given tangent. This is also a given tangent, y equal to tan theta x. We have to prove the moment of inertia is 5 over 4 mp square. We should have the idea of moment of inertia. What is moment of inertia? To speak simply, the moment of inertia of a particle whose mass is m and distance of this particle from the axis of rotation is r, then moment of inertia of this particle is equal to mr square, and also moment of inertia emerges from the rotational motion of any particle or any body. In rotational motion, this term emerges, that is moment of inertia emerges when body is rotating or particle is rotating about an axis. Now moment of inertia is equal to the product of the mass and square of its distance from the axis of rotation. Now to find out the moment of inertia of this lamina, at first we take an elementary rectangular area, that is whose length and breadth are del x and del y. This is this length is del x and this breadth is del y. So the area of this rectangle is del x del y, and elementary rectangle we take an elementary rectangle to P and to Q and R, point Q and R, whose coordinates are coordinate of Q is xy and coordinate of R is x plus del x and y plus del y. Also Q and R are two neighboring points, to nearest to each other. They are too much nearer to each other. And also the area of the elementary rectangle is del x del y. Rectangle of area del x del y, and also we consider the surface surface density of the lamina as rho equal to mass per unit area, that is total mass is given, which is m over the area of the lamina. Area of the lamina is pi. This is the surface density rho equal to m over ab. So the mass of the elementary rectangular region elementary rectangle is rho into del x del y, product of rho, del x and del y. This is the mass of the elementary rectangle, that is point mass. It is also considered as point mass. Now, at first, we find the moment of inertia of this point mass above the diameter. So, moment of inertia of rho del x del y, that is point mass, whose mass is rho del x del y, is rho mass into square of the distance of this point mass from the diameter. So moment of inertia also we have to write moment of inertia of the rectangular elementary rectangle whose length and breadth are del x del y, which are infinitesimal. Too much small rectangle, that is elementary rectangle, and moment of inertia elementary rectangle above the diameter is mass, that is mass is rho del x del y into square of the distance of this elementary mass, that is point mass. It is considered as point mass, and square of the distance of the point mass from the diameter, perpendicular distance, the point mass. Also the perpendicular distance is, equation is here, y minus tan theta x, y minus tan theta x over root over of 1 plus tan square theta whole square. This is the moment of inertia of this point mass above the diameter, which is rho del x del y into y minus tan theta x over root over of 1 plus tan square theta square. This is the moment of inertia of this point mass above the diameter. Now we have to find out the moment of inertia of the entire lamina. Moment of inertia of the entire lamina above the diameter, and it can be derived by integrating this moment of inertia of elementary rectangular point mass. If we integrate the point mass, integrate the moment of inertia of the point mass throughout the region of the lamina, we can get the moment of inertia of the entire lamina. So, moment of inertia of the entire lamina about the diameter. So, moment of inertia of the entire lamina about its diameter y equal to x tan theta is that double integration, that is double integration throughout the lamina over the lamina is rho del x del y minus x tan theta by root over of 1 plus tan square theta square equal to double integration throughout the lamina rho. If you simplify this term, we get x sin theta minus y cos theta over whole square over 1 plus tan square theta. This is, if you simplify this term, we get this is x sin theta minus y cos theta square. This is the simplified form of this term. X sin theta minus y cos theta square into over dx dy integration, double integration rho x sin theta minus y cos theta square dx dy. So double integration over lamina rho x square sin square theta plus y square sin square theta minus 2xy sin theta cos theta dx dy. This is the moment of inertia of the entire lamina about the diameter y equal to x tan theta. Now at first we find the integration. We find the integration. At first we find the integration, double integration over lamina rho x square sin square theta dx dy. We can use the rule of double integration. The rule of double integration is to integrate this term with respect to x when y is treated as constant, or respect to y when x is treated as constant. So we can integrate this term by rule of double integration. We get the range of x is minus a to a. The range of y is, we can use the relation, that is equation of the curve is, equation of the release is y equal to plus minus c by a root over of x. This is the limit of y. This can be regarded as the limit of y minus d by a root over of x square minus x square, d by a root over of x square minus x square, x square sin square theta dy over dx. Now, this is the rule of double derivation into rho. So, rho into sin square theta minus a2 plus a x square y minus b by a square minus x square d by a to power of a square minus x square dx. If we put the limit of y in this term, we get rho sin square theta minus a2 plus a x square into 2b by a to power of a square minus x square dx. Now, we shall integrate this term with respect to x. To integrate this term, we put x equal to a sin theta, y equal to dx equal to a cos theta d theta. So, when x equal to minus a, theta equal to minus pi by 2, x equal to plus a, theta equal to pi by 2. So, rho sin square theta minus pi by 2 plus pi by 2 a square sin square theta into 2b by a into a cos theta into a cos theta d theta. So, rho sin square theta x. We also put here a sin phi other than theta. A sin phi, a cos phi, also this is phi, which is phi, and this is phi, phi, phi. This is and rho sin square theta into 2b a cube into sin square phi cos square phi d phi. Rho sin square theta into 2b a cube over 4 and sin square 2 phi d phi. Now, this is also can be written rho sin square 2b a cube over 4 into b a cube 2 sin square 2 phi. 2 sin square 2 phi equal to 1 minus cos 2 phi. Cos 2 phi. And also the limit is minus pi by 2 to plus pi by 2. Minus pi by 2 to plus pi by 2. Rho b a cube over 4 sin square theta. If we integrate this term, we get pi minus sin 4 pi over 4 minus pi by 2, and value of this integral is rho b a cube sin square theta over 4 into pi, and this term is 0. So this is the integration of rho double integration rho x plus sin square theta dx here. So we have got double integration over lamina rho sin square theta x square dx dy equal to rho b aq pi sin square theta over 4. In the similar manner, we can also get rho lamina rho cos square theta y square dx dy equal to rho a dq cos square theta over 4. In similar way, we can find out this double integration as this, the value of the double integration as this, and also over lamina minus 2 rho xy sin theta cos theta dx dy equal to 0. It can be easily verified. The value of this double integration is 0. So, value of the moment of inertia of the lamina about the diameter is rho b aq pi sin square theta over 4 plus rho a b cube cos square theta over pi over 4. This is the moment of inertia of the entire lamina about its diameter. This equation is y equal to x tan theta. Now we have the equation of the tangent is x equation of tangent is x cos alpha over a y sin alpha over b equal to 1. So its gradient is minus b by a cot alpha. This is the gradient of the tangent, and also the gradient of diameter. The equation of diameter is y equal to x tan theta. So gradient equal to tan theta. As the tangent and diameter are parallel to each other, so their gradient are equal. So we can write minus b over a cot alpha equal to tan theta. That their gradients are equal because they are parallel to each other. Tangent and the diameter are parallel to each other, so their gradients are equal. Now, we also write the distance of the tangent from the center of the lamina is equation of the lamina is y minus x tan theta. So distance from origin, that is distance of the center of the lamina. The coordinate of the center of the lamina is 0, 0, that is origin. So distance of the center of the lamina from the perpendicular distance of the tangent from the center of lamina is the equation of tangent is this. So its distance from the origin is 1 over integral of cos square alpha sin square alpha d square. This is the distance of the tangent from the center of the lamina, perpendicular distance of the tangent from the center of lamina, which is given as p. So 1 by 1 over p square equal to cos square alpha over a square sin square alpha over b square. If we divide the right hand side and left hand side by Sine square alpha we get 1 over t square cosec square alpha equal to cot square alpha 1 over t square cot square alpha plus 1 over t square. So 1 over t square 1 plus cot square alpha equal to 1 over t square cot square alpha plus 1 over t square. So cot square alpha 1 over t square minus 1 over t square equal to 1 over t square minus 1 over t square. So cot square alpha equal to t square minus b square over t square b square into a square t square over a square minus t square. That is, t square is cancelled out. So we can get a square over b square into t square minus b square over a square minus t square. And now we have already got b square a square cot square alpha equal to tan square theta. So tan square theta equal to b square over a square into value of cos square alpha is this. So we can put this a square over b square into t square minus b square a square minus b square are cancelled out. So tan square theta value of tan square theta is e square minus b square over a square minus b square. Now we can write sec square theta equal to 1 plus tan square theta 1 plus tan square theta value of tan square theta is this b square minus b square a square minus b square equal to a square minus b square over a square minus b square. So cos square alpha equal to a square minus b square over a square minus b square. Also sin square alpha equal to 1 minus cos square alpha 1 minus this equal to this is equal to p square minus b square over a square minus b square. These are the values of sin square alpha and cos square alpha. We have already got the moment of inertia of the lamina about diameter is rho b aq pi over 4 sin square theta plus rho a bq over 4 pi cos square theta. If we put the values of cos square theta and sin square theta, and sin square theta in this term, in the term moment of inertia, we get rho. We have also factorized this term, this expression. After factorization, we get rho ab pi over 4 into a square sin square theta plus b square cos square theta. Rho ab pi over 4 a square into sin square theta value square theta. There are also sin square cos square theta. It is wrongly written. This is cos square theta and this is sin square theta. Value of sin square theta. A square into sin square theta is value of sin square theta is p square minus b square. A square minus b square plus b square into cos square theta is a square minus b square over a square minus b square. So this is rho ab pi over 4 a square b square minus a square b square plus a square b square minus b square over a square minus b square. This term are cancelled out. And we get rho pi ab rho ab pi over 4 b square into a square minus b square over a square minus b square. This is cancelled out. So ultimately we get rho ab pi over 4 into b square. Now the moment of inertia has been got as moment of inertia of lamina about diameter is rho ab pi over 4 into p square. Now we have considered the density of the lamina as rho, and rho is equal to mass per unit area. Mass is m, area is pi ab. So mass equal to rho ab pi. So we can put rho ab pi as m, that is m p square over 4. This is the moment of inertia. This is the moment of inertia of the entire lamina about its diameter in equation of given y equal to x tan theta. Now finally we have to derive the moment of inertia. Moment of inertia of lamina about diameter about the diameter of the lamina about the diameter of the diameter lamina of the diameter about its tangent whose equation was regarded as x cos alpha over a y sin alpha over b equal to 1 is what is the value of moment of inertia about its tangent, that is about its tangent. The moment of inertia of the lamina about its tangent x cos alpha over inertia of the lamina about its tangent. So the equation is this. And how can it be derived? It can be derived by using the theorem of parallel axis theorem on moment of inertia. We use the parallel axis theorem on moment of inertia to evaluate the moment of inertia of the lamina about its tangent. What is parallel axis theorem? The parallel axis theorem is that the moment of inertia of any body is equal to the moment of inertia is equal to the sum of the moment of inertia of this body about a axis through its center of gravity plus mass into square of the distance of this body from the square of the distance of the center of gravity from the other parallel axis. Two parallel axes. One is passing through the center of gravity of the body, and other is not passing through the center of gravity. Other than center of gravity, passing through the points other than center of gravity. These are two parallel axes. The theorem of moment of inertia on parallel axis is the moment of inertia of the body about the parallel axis, which is not passing through the center of gravity, is the moment of inertia, sum of the moment of inertia of this body about its axis passing through the center of gravity of it, and plus the product of the mass and the square of the distance of the center of gravity from the other axis. Perpendicular distance, square of this perpendicular distance from the other axis from the center of gravity. This is the parallel axis theorem. So we can use the parallel axis theorem to derive the moment of inertia of the lamina about its tangent. So moment of inertia of the lamina about the tangent, by using parallel axis we can write the moment of inertia of the lamina about its diameter, which is passing through its center of gravity, which is mp square over 4 plus product of mass into square of the distance of the center of gravity from the perpendicular distance of the center of gravity from the tangent, which is given as P. So m into p square. This is derived by using the parallel axis theorem on moment of inertia. So if we sum of these terms, we get 5 over mp square. This is the final moment of inertia of the lamina about its tangent. Thus, we can derive the moment of inertia of the elliptical lamina about its any tangent, which is parallel to its diameter, whose equation is y equal to x tan theta, is 5 over 4 mp square. This is the moment of inertia of the lamina about its tangent. So this is derived by this way, and also we use the parallel axis theorem to evaluate the entire moment of inertia of the lamina about its tangent. Thanks for watching this video. See you next week.